The AP exam is just days away, if not just hours away by the time you're watching this. Let's talk about some of the biggest ideas and the FRQs that you are likely to see on Tuesday morning's exam. My name is Corinne. I run Chem with Corinne. The goal of all of my accounts is just to help make chemistry as approachable and understandable as possible so that you can survive and thrive in AP Chem this year. So here's the plan. I just went live and the session was popping. There were so many students in the chat. It was awesome, but I didn't quite go over what I wanted to go over. So I'm going to record this video. Hopefully it'll be nice and short so you can still get an idea of what I wanted to cover tonight. So the plan is to focus on the big ideas. We're going to actively engage with some FRQs. And I want you to walk away from this just feeling more confident in all the work you put into this course this year. So these are the buzz phrases that we're going to start with because these are the things that you are likely to see in multiple places on this exam. The first one is effective nuclear charge. You've probably known it as ZF. Basically what it is just a really simple idea. So it's this idea that as I move from left to right across a row, I am adding protons to the nucleus of the atoms. As I add protons, I'm increasing the magnitude or the amount of positive charge. When I do that, the electrons are attracted to that higher quantity of positive charge. So basically, it's like thinking of a magnet. I have a stronger magnet the more protons I have, and the closer those electrons are going to be pulled toward that nucleus. So basically, the greater the effective nuclear charge, the smaller the atomic radius, and the harder it is to move an electron because it ties back in to Coulombic attraction. Let's roll that into the second buzz phrase, Coulombic attraction or Coulomb's law. So what I've drawn on here, this is Coulomb's law. It is on your formula sheet, so that's nice. It's just that the electrostatic force, which is either the attractive or the repulsive force between two charged particles, is directly related to the magnitude of charge and then inversely related to the square of the distance between those charges. So basically, the larger the magnitude of charge, and what do I mean by that? Like magnesium with +2 has a stronger attractive force than sodium with a +1 charge. So the greater the magnitude and the shorter the distance between those particles, the greater those forces are. When it comes to distance, you're looking at the radius of that ion or that atom. So the smaller the ionic radius, for example, the more tightly all of those ions can pack together. The closer those charges are, that means the stronger the attractive or repulsive force is. So that's how those two come together. So as the effective nuclear charge increases across a period, Coulombic attraction also increases, which is why ionization energy increases, right? It takes more energy to remove those electrons that are attracted towards that nucleus. If you want to find out more, I'm going to link all of these video notes. You can actually see them in the description right now. Anytime you see like a little video or a little laptop, know that you can click on that and watch a quick tutorial on that topic. All right, let's move into the next one, sliding into equilibrium. Q versus K. You're probably really familiar with K, but there's a good chance you may have forgotten what Q is. Q is the reaction quotient, and the good news is it's calculated in the exact same way as K. The difference is it is that relationship between products and reactants at any point other than equilibrium. So what we need to be able to do is compare Q and K and kind of determine like where the reaction is heading. So if Q is greater than K, the reverse reaction is favored and the formation of reactants is favored. If Q is less than K, the forward reaction is favored. We're forming more product. And if Q is equal to K, that just means you happen to be at equilibrium. If the reaction is at equilibrium, the magnitude of K is going to tell us which side of that reversible reaction is favored. The thermodynamically favored process is a product's favored reaction, where K is greater than 1. If K is less than 1, the reverse is favored. And if K happens to be equal to 1, then there is something that's actually equal at equilibrium other than those rates. It's the concentration of products and reactants. But again, that doesn't happen too often. All right, rolling into number 4, which is thermodynamic favorability, or TDF. These are the quantities that you just need to have memorized. So a negative enthalpy, a positive entropy, a negative Gibbs free energy, those all tie into the Gibbs free energy equation. Delta G equals delta H minus T delta S. With enthalpy, right, we are looking at the difference between the energy of those reactants and products. If the products are at lower energy, then we have a negative enthalpy. That's an exothermic reaction. That's what the universe favors. When it comes to entropy, I'm looking at my desk right now. Maybe I'll reveal like the ridiculous mess that is surrounding me at this point of the year. If I hit my my hours on YouTube. But basically, a positive entropy or an increase in entropy is what, again, the universe favors. Gibbs free energy, that's the work required to, that's the work available to do work. Ideally, we don't need any work, right, for a reaction to happen. So that's why we're aiming for that negative delta G value. When it comes to the equilibrium constant, we're looking for a products favored reaction, and then we'll talk about cell potential and electrochemistry soon enough, but we're looking for a positive E cell value. All right, let's look at an example. So this reaction is not thermodynamically favored under standard conditions, but it becomes favored as the temperature decreases. Which of the following is true at standard conditions? So we have to think back to what is favored. We know we want a negative delta G. So under normal conditions, this would give us a positive delta G. But as the temperature decreases, then it's actually favorable. So look at these answer choices. Try to figure out what you think would be true. All right, I'm going to give you one more second. So this would only happen if both the entropy and the enthalpy are negative. So what I would do in a situation like this is I would cross out answers that are very wrong. So we know that if S is negative and H is positive, those are both opposite of TDF conditions, right? That is never favorable at any temperature. And then if we think about delta S being positive, delta H is negative, that would be thermodynamically favored at all temperatures. So that leaves us between A and B. And that's when you want to think about the Gibbs free energy equation, right? Delta G equals delta H minus T delta S. We're looking at that T and delta S there, trying to figure out how we can get a negative delta G overall. There are going to be questions like this. Maybe you're going to have one where a student has made a prediction about the thermodynamic favorability, and you have to decide whether or not their prediction was accurate, just things like that. So feel really comfortable with this and using this relationship. And also, like, you can say TDF if you want to. That's a pretty common abbreviation. So with abbreviations, with your FRQs, what you want to do is you want to just define the abbreviation at least 1 point per question. So if you define it in part A, the same reader is going to read parts A through F in that long FRQ. Just make sure you define it with parentheses, and then you can use that abbreviation. All right, so now let's talk about IMF, because this is another big topic that you're going to see over and over again. So let's just review intramolecular versus intermolecular. So intramolecular, those are the forces within a substance. Those are the bonds, the covalent, ionic, metallic bonds, network covalent bonds, all of those bonds actually inside those molecules. Versus intermolecular, those are going to be the interactions between particles and molecules. And understanding like what each of these looks like, how to determine the strength of these, how to rank the strength of those, things like that. That's what you need to know with IMF. So these are just examples of different types. The strongest type of IMF is going to be an ion-dipole interaction. We don't normally see these, however, we did on last year's FRQ, so it's good to review it. So ion dipole, it's just like it sounds. You're taking an ionic substance, you're dissolving it in a polar solvent, so it separates out into its ions. As you can see, the chloride ion is interacting with the partial positive on hydrogen. The sodium ion is interacting with the partial negative on oxygen. The other type of IMF is going to be a dipole-dipole interaction. So in a dipole-dipole interaction, we just have the interaction between two polar molecules. And we can also have hydrogen bonding, which is a specific type of dipole-dipole interactions. It's stronger than dipole-dipole interactions, where hydrogen in a polar molecule interacts with a very electronegative atom, either oxygen, nitrogen, or fluorine. But again, you have to have one of those three atoms attached or bonded to hydrogen, and hydrogen has to be in a polar bond. So you can't have hydrogen bonded to carbon interacting with those electronegative atoms. It has to have an actual dipole for this to happen. The other type of IMF, and everything experiences this, is London dispersion forces. This IMF is just based on the random movement of electrons. So randomly, you're going to have a high density of electrons in one portion of the molecule or atom, leaving the other side with, a partial positive charge. So this IMF sounds like it wouldn't be very strong, but this is actually the IMF that's the reason that geckos are able to scale walls. So surprisingly, it is a lot stronger than you'd expect. And that leads into understanding also, how do we know how to rank the strength of these? So when it comes to London dispersion forces, we're looking at the polarizability of that electron cloud. So what that means is, if I think about a situation where I have a molecule that has 5 electrons versus one that has 55 electrons. If I have 5 electrons hanging out together versus 55, there's going to be a bigger difference in those when I have 55 electrons. That is a more polarizable electron cloud. When I have 55 electrons congregating together to create that partial negative, leaving that partial positive, there's going to be a much bigger difference in those two dipoles. So the larger the molecule, the more electrons it has, the stronger its LDF. When it comes to the other IMF, when we're looking at hydrogen bonding, we're looking for a number of sites for hydrogen bonds to occur. And dipole-dipole interactions is based on the polarity of that molecule. The more polar the molecule, the stronger the dipole-dipole interactions. So a lot of the FRQs are going to just be asking you to justify. Maybe they even tell you exactly which IMF a molecule experiences, and you just have to explain, oh, well, though these both experience LDF, dipole-dipole interactions, hydrogen bonding, this one has 2 more sites for hydrogen bonding. The more locations for hydrogen bonds to form, the stronger those intermolecular forces and the more energy that's required to disrupt those for a phase change. Just something along those lines. All right. Oh, and I guess I jumped the gun. This is just an overview of that. So talking more about polarizability. Polarizability is another buzz phrase, but it's just understanding that, the more electrons you have, the greater that difference and the stronger that London dispersion force. All right, these are the equations to memorize before Tuesday's exam. I just posted like a full video on all of these. The ones at the top two, the top 2 are the ones that you definitely want to focus on because those ones are not on the equation sheet. So the cell potential is equal to the cell potential at the cathode minus the cell potential at the anode. You can get to this through stoichiometry, but I think it's a lot easier just to memorize this equation. So remember that the cathode comes first. And then with the enthalpy of reaction, this is a tricky one. When you calculate the enthalpy, the entropy, so the enthalpy of formation, the entropy or the Gibbs free energy, it's always products minus reactants. The one equation that's not on the formula sheet, of course, would be the one that's reactants minus products. So if you are looking at a problem and you're trying to solve for the enthalpy of the reaction based on those bond enthalpies, you always have to remember it's the sum of the bonds broken, which are the reactants, minus the sum of the bonds formed, the products. The molar heat of solution, this is one that students are often asked and they get stuck on it. If you get stuck on this, it's always going to give the units as either kilojoules per mole of reaction or joules per mole of reaction. Recognize that that's the joules per mole. So even if you have no idea how to solve a question, you can use those units to work backwards. Everything else on here is just kind of a combination of 2 equations or just a rearrangement. Again, just things to have memorized so that your life is a little bit easier when you sit down to take this test. All right, so other things to know about this exam. So you are taking a hybrid exam in 2026. What that means is all of your MCQs will be on the screen, but you are going to have a paper copy of the periodic table along with the equation sheet. So you'll have that, you'll have scratch paper, you'll have your calculator. You do not have to clear the memory on your calculator, and you want to go in with pen and pencil, whatever you feel best about. Do not use an erasable pen though, because there's a chance that at some point your FRQ booklet could end up in a hot spot where all of a sudden your ink is gone. Okay, so do not use an erasable pen or anything that could be lost in transit, basically, as your exam makes its way over to where the reading's happening. Other things to know. So the 5% rule always applies. Might not be the case if you go on to take additional chemistry classes, but you will not need to use the quadratic formula for any of those equilibrium questions. You don't even have to justify the 5% rule. You're just going to negate X and move on. Throughout the exam, I suggest using 3 sig figs. There is one hidden point for sig figs somewhere in the FRQs. It's not going to be mentioned in the actual problem. It's just something that will be on the scoring guide. So it's a surprise, right? A bonus. So it's a safe bet just to use 3 sig figs throughout. I just wouldn't waste time on sig figs. You don't have a lot of time, right? That's the hardest part of taking this exam. So make sure you're not wasting time on sig figs. Always check out the units that you're given in the problem. What is the question asking for? Make sure that you're actually solving for that quantity. It's the biggest hack in chemistry is to work backwards from the units. And if you're completely stuck, go to your equation sheet, right? Like use your equation sheet, find the equation you need, look at the constants, and then work from there, right? The ideal gas constant. We have liters per atmosphere per Kelvin per mole. Oh wait, I got to convert Celsius into Kelvin. Use the units to help check your work. Also recognize that you want to answer every single question. So I recommend a 3-pass system. Go through, answer all the questions you can answer quickly and easily so that you're not, wasting time, spending 5 minutes on a single MCQ while you're spiraling and all of a sudden your confidence is gone, right? Mark that in Blue Book or put it on your scratch paper and come back to it. Also recognize with these FRQs, especially the long FRQs, even if you have no idea how to answer parts A through C, put in a little note, say, assuming an answer of 2.4 moles from answer choice B. If you then continue on to complete that work correctly, even with a wrong number, you will get full credit. Okay, so realize that part of taking this test is dealing with some of the anxiety that comes with looking at something and recognizing, oh, I don't remember how to do this. How do you handle that? How do you come back from that? Okay, I want you taking deep breaths and doing the easy stuff first. You see a particle diagram, take a second to count up those particles and just kind of reset. All right, so what not to say is just as important as knowing those buzz phrases. I do not want to hear that anyone said like dissolves like, opposites attract, or based on the atomic radius trend, this element is to the left of that. No, don't say any of that. You're actually going to justify all of your answers because you know so much chemistry. Like dissolves like. What does that mean? Two substances that have similar IMF are going to be miscible in one another. They do mix well with one another. Opposites attract, right? Knowing that like a positively charged cation is going to like thinking about what's happening in those bonds, not just saying opposites attract. And then when it comes to those trends, actually understanding what is happening with all of these trends. We already talked about effective nuclear charge, right? Understanding that the atomic radius is kind of the start of all of it. And from there, we're looking at Coulombic attraction, looking at the ionization energy. As the atomic radius decreases, ionization energy increases. What's happening with electronegativity, being able to justify all of it, not just saying, oh, well, oxygen is to the left of fluorine, so that means it has a lower electronegativity. Why? Why does it have a lower electronegativity? Be able to explain that. And in case you haven't picked up on this yet, the goal of my accounts is just to help as many students as possible. So the things that you add to the chat are going to help other students out. I learned some like really cool memory tricks on some of my videos I've posted recently that I had never heard of. So thanks for sharing those. Please keep sharing them. Let's keep helping each other as we tackle this difficult course. All right, moving on. If you look at the video notes, I just posted a new FRQ problem set. A few days ago, I made my predictions about what we were going to see on the FRQs, and then last night, I decided to make this problem set so that we could have some practice with the types of questions that I anticipate we're going to see. So I'm probably going to go through all of this in depth in another video, but I do want to just take some time to like go through some of these big ideas too. All right, so this first one is just going to be a good review of kinetics because it's probably been a while since you've done some kinetics. So looking at this question, go ahead and pause this video here, take a second to look at it. Don't get overwhelmed by all of the data. Instead, go straight to part A and read what you're going to be solving for. All right, so you should have determined we need to find the rate law. So the rate law, again, is going to be the rate with respect to the reactants that describes how quickly we are forming all of those products. So what we want to do is we want to look at the data we're given, find situations where each reactant is held constant and the other one is changed, and see how that changes the rate. So that's what we're going to do. We're going to find the rate with order to O3, ozone, and with order to NO, that nitrogen monoxide. So we're going to do that. We're going to look at the rates and then write out our rate law. So rate's going to be equal to K times the concentration of, let's see, let me look at this for a second. I don't remember the answer. Times the concentration of O3. So what we are doing here is we're looking at trials 1 and 2 where O3 is held constant and NO changes. When the concentration of NO doubles, then the rate also doubles. So that indicates first order kinetics. When I look at O3, So if I look at trials 1 and 3, then NO is held constant. When the concentration of O3 is cut in half, there's no impact to the rate. So what that means is that it is 0th order with respect to ozone O3. And what that means is it's not going to be included in the rate order because it doesn't actually influence the rate of production of products. So our rate law is going to be rate is equal to K times the concentration of NO. For part B, we want to find the rate constant, and we want to give the appropriate units. That's the hard part here. So we want to then just plug in values. It doesn't matter. You can use trials 1, 2, or 3. I tend to stick with trial 1 when I'm working with experimental data because oftentimes those are the smallest numbers. But it does not matter at all. Plug in those values, solve for K. You do have units given in that table, so you can just plug those in. Or you can remember when it comes to units of K, and this is something I just learned from you all, use the concentration raised to the power of 1 minus order times the time, the inverse time. And when it comes to units of K, this is a really great hack that I actually just learned from you all. So you're going to take the concentration raised to the power of 1 minus the order of the reaction times the inverse time. So in this case, it would be inverse seconds. But that could be minutes, it could be hours. Just keep track of your data. All right, moving on to particle 2. So I definitely think you're going to see some particle diagrams. You have to make predictions. You have to see if the particle diagrams are written correctly. What you're going to do when you see a particle diagram is you're going to take a second, take a deep breath, and you're going to count up and label all of the things that you see in that diagram. So in this case, I have 2 molecules of H2, 2 molecules of N2, and 5 molecules of NH3. That's where I'm starting. Then I'm going into the instructions. In part A, I'm asked to calculate Kp. So I know that each substance has a partial pressure of 1 atmosphere. And then I'm just calculating Kp. So Kp is my equilibrium expression with relation to pressure of these gases. So I'm going to have the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. So I'm just plugging all of those values in to get my Kp value. And the nice thing about Kp, capital K, is there are no units associated with the equilibrium constant. Not the case with the lowercase rate constant we just looked at. But when it comes to equilibrium, you do not need to worry about units, thankfully. And then part B, when the temperature is increased, will the value of Kp increase, decrease, or remain the same? So then what I'm going to do, this is a Le Chatelier's problem. I'm going to look at that delta H of formation. I see that it's exothermic, so that means heat is being released as a product. When the temperature is increasing, I am adding heat as a product. Therefore, I'm going to favor the reverse reaction. So when I think about my Kp expression, if I'm favoring the reverse reaction, I'm increasing the pressure of those reactants in my denominator. When I do that, Kp decreases. So it's when you have questions like this, think step by step. How does this one change impact my calculation? Or, how does this impact the experiment? Just step by step. If you need to throw some arbitrary numbers in there, do it. Whatever it takes to get you where you need to be. All right, so that's just an example of a particle diagram. This is really similar to one that we saw last year. So we'll probably see something that's not related to Dalton's law. All right, number 3, buffers. I threw a lot of acid-base chem in this because I think that's what everyone's still stressing about. So this one's about malic acid. It's actually used pretty often in the food industry. So we have malic acid and we have monosodium malate. We're given the concentrations of each. We have the Ka. And what do we do now, right? What you're always going to do is just start by writing that dissociation equation. So that's dissociation, we're just showing what happens when that acid loses a proton in solution. So you're subtracting a proton, and then whatever you have left, you're just subtracting 1 from the charge. So that goes from neutral malic acid to C4H5O5 minus. The acid becomes the conjugate base, so that second product is our conjugate base. So now what we're going to do is we're going to pull those concentrations from the problem. And the question is, wait, where did sodium go? Sodium is a spectator ion, so I'm not worrying about that in this. My concentration is going to be 0.023 of the conjugate base, the C4H5O5 minus. If it really bothers you, you can include sodium in there, but that's just a spectator ion. The other thing I know is my Ka value that was given. So now what, right? So now if I was stuck I'd probably be thinking like, oh, it's time for a rice table. But this is a buffer problem. You're going to go to your equilibrium section. You see the very last equation listed, the Henderson-Hasselbalch equation. So you can use that for this problem, and it's going to make your life so much easier. The pH is equal to the pKa plus the log of the conjugate base over the conjugate acid. We're going to use concentration in this case, but if we are looking at a buffer system, we could also just use moles if that's what we were working with. So we're just plugging all of that in to get our final answer of a pH of 5.89. So that's how we would solve a simple buffer problem without, again, like I said, you could still rice this out and you would get the same answer and you get full credit either way. I think that's one of the hard things about acid-base chem is sometimes there are multiple ways to get to the correct answer. All right, now looking at KSP. So again, this is something that I do think we'll see this year. It's been a couple years since we've seen this. So the nice thing is you're not going to just have to, right away figure out whether or not a precipitate will form. The FRQ is going to be broken up into pieces like this. So the first thing we want to do is write the expression for the dissociation. So again, with these, you have to include the charges, you have to include the states, and they have to be balanced. In this case, it's 1-to-1, so that's pretty easy. And let's say you don't remember the charge of sulfate, that polyatomic ion. Always work backwards. So in this case, we have our cation, Ba. It has a charge of 2+, so that means the sulfate has to be 2-. So include all of those charges and states in this dissociation equation. And again, because we're dealing with Q and K, we're probably going to have a reversible reaction here, right? So we will be using the reversible arrows. In part B, we want to write the expression for the KSP, which we already know K is concentration of products over reactants raised to the power of their coefficients. However, look at the state of our reactant in this. It's a solid, so solids and pure liquids do not impact equilibrium. Therefore, your KSP is always just going to be the concentration of whatever those products are in that dissociation equation. And now what we have to do is we have to calculate QSP. Again, QSP is calculated in the same way. It's just at any point other than equilibrium. So what I'm going to do now is I'm going to go back into that problem. I see a bunch of concentrations and volumes. I know I'm using MV equals moles. So we want to determine the number of moles of each and then divide by the total volume of the solution to find the new diluted concentration, right? Again, we're ignoring spectator ions here. So in this case, we have Na and Cl minus. Those ones we're just not going to focus on. We're just focusing on the concentration of Ba2+ and SO4 2-. So this is how we then solve for those concentrations, then plugging all of that in to get our QSP value. Last step, we want to compare Q versus K. K we were given in the initial equation, in the initial question as 1.10 times 10 to the minus 10th. So our Q value is bigger than K. What that means is the reaction is favoring the reverse reaction. We're favoring the formation of reactants. And you're like, okay, so we're not going to form a precipitate. Look at your dissociation equation. Be careful with this. The reactant is a solid. So yes, we are favoring the reverse reaction or the formation of those reactants, but that's where our precipitate is. So therefore, this would form a precipitate. All right, moving on to number 5. A lot of students really stressed about electrochem. If you have not learned electrochem yet, these are the types of questions that I expect us to see. I do think we'll see an electrolytic cell this year because we just haven't seen that. And I'll spend some time going through all of that in just a second too. All right, so with a question like this, you're going to be given, if you're given a table of values like this, they are always reduction potentials. A redox reaction, though, is not just a reduction reaction, right? It's also the oxidation. So we have to look at these values and recognize one of these is a reduction, one is an oxidation. So look at the one that is the least positive. That is your oxidation reaction. We're going to flip that reaction around so that we can then balance out our electrons. So we flip that first half reaction. We then have to multiply the reduction by 3 so that our electrons cancel out. Then we just add those together. And this is probably a lot simpler than a lot of the reactions you've balanced. This is all we tend to see on the AP exam. It's nothing too complicated. You will never have to balance in acidic or basic solutions. That's not covered in the AP curriculum, even if you did it in class. The next thing we want to do is calculate the cell potential. And again, for whatever reason, this equation is not on the formula sheet, the cell potential is equal to the cell potential at the cathode minus the anode. So remember, cathode comes first. So while I did flip the equation, I'm just going to use those values from the reduction potentials. If you end up flipping the sign of that, then you would just add these two together. So we get an overall cell potential of 2.476. That's a very positive value, so this is a thermodynamically favored cell. All right, last one, we want to calculate delta G. So when you look at the last section of the formula sheet, we have quite a few equations for delta G. This is the one we want for this one. So N is going to be equal to the moles of electrons from that balanced redox reaction. We're multiplying by the Faraday's constant and then multiplying by our cell potential. So we multiply all of that together, and that gives us an answer in terms of joules per mole. So, and the reason I know it's joules is because I look at the formula sheet, I see that 1 volt is equal to 1 joule per coulomb. So I've calculated that. It's a really big number. That's because it's in joules. Questions asking for kilojoules per mole, I just divide by 1,000, and that gives me my answer. I do have a negative sign. That indicates that, again, this is a thermodynamically favored cell. So this is going to be a voltaic or a galvanic cell. All right, so Faraday's law, we could also see a question like this. We're going to be using a little bit of stoichiometry to figure out what's going on in that cell. So in this case, we have an electric current of 10 amperes that passes through the cell for 30 minutes. And we want to determine how much silver is deposited at that electrode. So we're using unit conversions on that formula sheet. We're seeing that 1 amp is equal to 1 coulomb per second. We know the Faraday's constant is 96,485 coulombs per mole of electrons. And we're just working from one number, and then we're just practicing with converting from one unit into another. It's really good practice with dimensional analysis. So going from minutes into seconds, seconds into coulombs, coulombs into moles of electrons, and then I go back to my balanced equation. For every 3 moles of electrons, I will deposit 3 moles of solid silver. And then last step, it's just going to the periodic table, finding the molar mass of silver. So you go through, you multiply all of that out, we will have deposited 20.1 grams of silver. The other type of question we might see is something where we're actually given the mass and we want to figure out how long the cell operates. But again, use your constants, set it up so that your units are canceling on the diagonal. All right, and the last type of question that I think we might see, this is a non-standard cell. I should have updated the title there. Sorry about that. There we go. All right, so if the concentration of Al3 plus increases from the standard concentration of 1 molar to 1.5 molar, how would the cell potential change? So this is known as the Nernst equation. It is on your formula sheet. You will never actually have to calculate that non-standard cell potential. But what you will have to do is predict whether it's going to increase, decrease, or stay the same. So what we want to do is we want to think, okay, if I've increased the concentration of Al3+, I've increased the concentration of my numerator. When I do that, my Q also increases. So now I'm subtracting a larger value from that cell potential, and my non-standard cell potential is going to decrease. So again, another situation where you have to think through step by step, how is this change going to impact my overall calculation? All right, calorimetry is on there every single year. Let's look at this problem. You might be given lab data, you might have to solve for missing data, something like that. It just kind of depends on the year. So with this one, we want to calculate the amount of heat released in the experiment. So right away, I'm seeing that word released. I know this is an exothermic process. I know I will have a negative value. So we want to assume the heat of the solution is the same as that of water. So when I look back at the actual problem, the dissolution of calcium chloride, if you see dissolution, what that means is I am dissolving something in water. This is going to be a situation where I'm adding up the mass of both to find Q. If I have a solid chunk of metal that I heat up and then drop into water and I'm measuring that temperature change, there's no reaction happening there. That's where we'd keep the masses separate. But in this case, we are combining those two. We want the total mass. So when we calculate the total heat, it's going to be a Q equals MC delta T, or a Q equals MCAT, whatever you have learned. Same equation, right? So we have our mass, which is 104.5. We have our specific heat, which is the specific heat of water. And then we have our change in temperature, which is the final minus the initial. So we're looking at that difference, and that will automatically give us a negative value. But because we're already calculating the heat released, we want to take the absolute value of that, right? So that's 3,320 joules are released. So now part B, this is the part that typically trips up students. We want to find the enthalpy of the reaction. And let's say you're like, I have no idea how to do that. I don't have an equation. Look at the units. So this is given in kilojoules per mole of the reaction. So we want to think about converting our calcium chloride into moles to figure out how much heat is released, right, per mole of calcium chloride that dissolves. A lot of students in the live asked, and I saw this afterwards, of course, why do we not include the mass of water here? Because we are looking at the mass of, so we're looking at the solute in relation to how much heat it releases, right? We're not looking, in this case, the water is the surroundings, right? So we're looking at the amount of heat total compared to the moles of solute. So what we're going to do now is we're going to take our 3,320 joules, we divide that by the moles, and we get a really big number because it's asking for it in kilojoules per mole. So take that number, divide by 1,000, and then be careful. This one asks for us to include our sign. Again, it's kind of given the heat is released. That's a sign that this is an exothermic process. We need a negative sign here. Also, our temperature decreased, right? So knowing that, that would also automatically give us that negative Q value, and we know that our delta H is going to be negative here. All right, moving into 9, I had to include IMF because we always see IMF. These structures, you would actually probably have all of the carbons and hydrogens drawn in, but I wanted you just to focus here on identifying the difference between these two. So looking at these, they all have, they have that at least 3 hydrogen bonding sites, and then adrenaline on the left also has that additional site. So because of that, because it has more sites for hydrogen bonding to occur, it's going to have a bigger web of all these connections between molecules. The stronger the intermolecular forces, the more energy that's required to disrupt or break those attractions between molecules. Therefore, the higher boiling point. In general, the stronger the IMF, the higher the boiling point, the higher the melting point. But the exception is going to be the vapor pressure. The stronger the IMF, the lower the vapor pressure is going to be. So make sure you remember that distinction. All right, number 10. So this is just a nice gas problem. So we have a sample of oxygen in a rigid container. When you see that, you're automatically going to think, okay, rigid, constant volume, and it's pressurized to 1.2 atmospheres. So I'm thinking, okay, this is either going to be ideal or this is going to be a combined gas law. In part A, it says if the temperature is lowered, okay, we're changing conditions. This is going to be combined gas law. Determine the pressure of O2. So I'm looking at my formula sheet. P1 V1 over T1 equals P2 V2 over T2. I can cancel out volume because it's constant, and I'm just solving for that new pressure, P2. In part B, I have in terms of KMT, kinetic molecular theory, explain what happens to the gas molecules as the temperature decreases. So temperature, what is temperature, right? Temperature measures the average kinetic energy of molecules. So the higher the temperature, the higher the kinetic energy of those molecules and the faster they're moving. So as the temperature decreases, there's a decrease in the average kinetic energy. So as molecule motion slows down, right, I will expect that there are fewer collisions and fewer collisions with the sides of that container. Therefore, the pressure is going to decrease. So kind of thinking through that. So KMT, what are we talking about, right? This idea, let's talk about like ideal gases. So an ideal gas is one that experiences no IMF. Its particle volume is essentially 0. It has completely elastic collisions where particles just, casually bounce off each other. No transfer of energy, no beef over that, right? They just move on. And that's leads into part C. So a student predicts that the actual pressure is going to be higher than the theoretical pressure found using the ideal gas law. Do you agree or disagree with their prediction and justify your answer? So with this, the actual pressure of a real gas is always going to be lower than an ideal gas. And that's because real gases experiences intermolecular forces. So because they have those interactions between the molecules, they are going to be attracted towards each other. Their pressure is going to be increased compared to this real gas. So I would disagree with this student and I would explain why. All right, and I added a bonus question. I like even numbers, but we're doing 11 because we need some acid-base practice. So salicylic acid, maybe you have an acne wash that has that in it. This is a weak acid that reacts with water to form an acidic solution. So what we want to start this one, we're starting off light. We want to start with the acid dissociation expression for this weak acid. So when this dissociates, it's losing an H plus ion. What are we left with? That conjugate base. So we just remove that H. We're losing 1 from the charge, so that now has a -1 charge. Next part, if the Ka of a 0.2 molar solution is 1 times 10 to the -5th, determine the pH of this weak acid. So now I'm looking at that acid dissociation expression, and I'm thinking, okay, Ka is equal to the concentration of H plus times the concentration of the conjugate base over that initial concentration of the weak acid. This is always true for every single weak acid because we're losing 1 proton at a time. So essentially Ka is going to be equal to X squared over the concentration of that weak acid, because again, the 5% rule always applies. You don't have to subtract X, you just ignore it. So that's going to be equal to X squared over 0.2. We then use that given Ka value to solve for that X, which is the H plus concentration. So the H plus concentration is 0.0141 molar. Plug that back into our pH equation, and we get 2.851. It looks like I have 4 sig figs there, but keep in mind with pH, your sig figs only count to the right of the decimal. So that 851 just has 3 sig figs there. But again, we're not stressing about sig figs, right? We're trying to use 3 to 4 throughout. All right. So now here's the hard stuff, the titration. So now I have 30 mils of that 0.2 molar salicylic acid. We're titrating that with 0.5 molar potassium hydroxide. With this, we'd still have the chemical formula. You'd probably be given the molar mass. College Board is great about giving you all of that, so don't think you have to have this memorized or anything like that. I just cut this when I was trying to stick this into this slide deck. So we want to determine the volume of 0.5 molar potassium hydroxide needed to reach the equivalence point. So what happens at the equivalence point? What is true? The moles of acid are equal to the moles of base. So what we want to do is we want to find our moles of salicylic acid and then make those equal to the moles of potassium hydroxide. This happens to be a 1-to-1 ratio, so we could use the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. But I encourage students to solve for moles of acid and then figure it out from there, just in case you have a 1-to-2 relationship. So we need 12 milliliters to reach the equivalence point. All right, so now if I went back, if we then wanted to determine the pH after 6 mils of potassium hydroxide has been added, we're going to think, well, wait, that's half the volume it takes to get the equivalence point. I know what's happening at the half equivalence point. The pH is equal to the pKa. So at the half equivalence point, the concentration of weak acid is exactly equal to the concentration of the conjugate base. Because of that, it cancels out in the Henderson-Hasselbalch equation. So you're just left with pH is equal to the pKa. So I take the negative log of my Ka value and I have my pH. And someone asked in the live, and this is a really good question, at the half equivalence point, is the pH also half of the pH at the equivalence point? No. So the only thing that it's half of the volume to get to the equivalence point. The pH is totally different though. So the pH here is equal to the pKa versus the pH at the actual equivalence point. We're looking at the excess conjugate acid or conjugate base in solution. That's what determines the pH. All right, and then the last part is the hardest part. So from there, I'm going to ask you to solve for the pH at that equivalence point. And as I just hinted, that's going to be based on the excess conjugate base in solution. So here's the process for that. You're going to find the moles of acid and base at the equivalence point. You're going to set up what's known as a BCA table, before, change, after. It's what we use when we're working with moles instead of concentration. So my acid and base are equal. I'm not going to have any of either of those left. We don't have a limiting reactant here. Then I'm going to add to my conjugate base. I'm going to end up with 0.006 moles of that conjugate base, and that's what's going to drive and determine pH. So now in step 2, I got to find the concentration of that. I look at my total volume. I had 30 mils of my weak acid, and I have 12 mils of my sodium hydroxide to get to that equivalence point. So 42 milliliters overall. I take my moles, I divide by the volume, that gives me my concentration. And now I'm like, okay, what do I do with that, right? So that's my initial concentration. I need my KB expression. So now I'm going to set this up. I don't have KB, but I do have Ka. And I know that Kw is 1 times 10 to the minus 14th. And if I don't know that, I'm going to find it on the equation sheet so that I can remember that. So you can quickly solve between Ka and Kb using that Kw, that autoionization of water constant. So now Kb, like Ka, is going to be equal to x squared over the initial concentration of that weak base. So I set that up, I solve for x, keeping in mind that x is hydroxide concentration. So I find my pOH, and then I have to remember pH is equal to 14 minus the pOH. You don't really have to remember it. It's on the formula sheet, but that's one of those like really simple steps and equations that students at this point in the year, you have so much in your brain that you don't think to do that, right? So like make sure that you're remembering to convert between pH and pOH depending on what the question's asking for. All right, so this is another bonus. I wrote this and then I was like, oh, this is probably like outside the scope, but let's just talk about, we haven't seen anything like this. It doesn't mean we couldn't see something like this. So, right? So a student uses 1 molar instead of 0.5 molar potassium hydroxide. She predicts this will decrease the volume needed to reach the equivalence point, but will not impact the pH. Do you agree or disagree with her prediction? And justify your answer. So again, step by step, let's think about how this change impacts everything else. So I have doubled the concentration. So if I double the concentration, I still need the same number of moles to get to the equivalence point. So I'm going to have the volume. All right, so if I have the volume, that doesn't really change anything, right, about the equivalence point, except it does. So if I have half of the total volume of that base, that means when I'm calculating the concentration of my conjugate base, that concentration is going to be higher, right? Because I have a lower volume. So instead of that 42 mils, I now have 6 mils less than that. So that's going to change my concentration of that conjugate base. When I change the concentration of the conjugate base, I am going to have a different pH overall. So this one, in this case, it's going to go from 9.076 as my initial pH to when I make this change, it becomes 9.111. So it is a small change, but technically we only agree with part of her prediction, right? It will decrease the volume, but it does slightly impact the pH. So be careful with a question like this. All right, if you are looking for more practice with all of the content, I'm just going to post all of these notes so you have access to them. I've spent a lot of time just going through the practice, but you're welcome to look through this. Last year, I went through a lot of the content in about an hour. I'll also link last year's Last Chance review so you can just, if you need just more help with the content, you can do that. All right, and electrochem is still the topic that I'm seeing the most requests for. So let's spend some time just reviewing electrochemistry before I close this out. So let's talk about the differences between the different types of cells, how to calculate the cell potential, the difference between the standard cell potential and the non-standard condition, and then electrolysis and Faraday's law. So electrochemical cells, basically it's just a device that's going to convert energy released by that redox reaction into electrical energy, or it's a reaction that takes electrical energy and converts that into chemical energy. So we have 2 different types of cells depending on the order. What are we doing here? Is this a thermodynamically favored reaction where we are producing electrical energy, or do we have to force this to happen in order to create chemical energy? So this is true for both types of cells. Oxidation is going to happen at the anode and reduction is going to happen at the cathode. The electrons are going to flow away from the anode and come to the cathode. If equilibrium is reached in an electrochemical cell, the cell voltage is going to be 0 because essentially at equilibrium, an electrochemical cell is a dead battery. Actually, I realize this is all about voltaic. I just combined galvanic and voltaic. This is about voltaic cells. So with a voltaic cell, we're going to have a negatively charged anode because this is happening naturally. And then reduction, the gain, that's going to be a positively charged cathode. The salt bridge is going to contain an inert or non-reactive solution. You have to have a salt bridge for this type of cell. And basically that's going to balance out the charge. So the cations are going to go to the cathode, the anions are going to move to the anode. And you don't need a salt bridge in an electrolytic cell. All right, so these are some of the things with electrochem. It sometimes can just be so counterintuitive. So there are a bunch of mnemonic devices to help you memorize kind of what's going on there. So oil rig or Leo goes grr just helps you remember that oxidation is the loss of electrons, reduction is the gain. And ox, red cat, tells you what's happening at each electrode. Oxidation happens at the anode, reduction happens at the cathode. For the movement of electrons, it's just a play on the first letter, right? Electrons come to the cathode and they move away from the anode. As a cell operates, the cathode accumulates mass. So the cat gets fat. This is true if you have something that is not an inert electrode. So if you have like a platinum electrode, something that is intentionally not meant to react, that's not true, right? Like it is not going to accumulate mass. But in general, the cathode is what is going to accumulate mass as that cell operates. So here are the two different types of cells that you need to know. On the left, we have the galvanic or the voltaic. This is the favorable, the positive cell potential spontaneous reaction where we are converting chemical energy into electrical energy. Versus on the right, we have an electrolytic cell. That's an unfavorable process where we are taking an external power source and changing that into chemical energy. I will say we haven't seen an electrolytic cell in a couple years, so I think we're due for another one of those. But here are the differences between the two. So for the voltaic cell, you'll see that salt bridge. We already talked about that. We have to balance out the charges. With an electrolytic, we do not need a salt bridge, but we do need some kind of external power source to force this non-spontaneous reaction to happen. When we think about the anode versus the cathode is where oxidation occurs, the cathode is where reduction occurs for both of these. But based on how this reaction is happening, the anode will be negative in a voltaic cell, but positive in an electrolytic cell. Same thing, cathodes are also going to be opposite. So right there, the cathode is going to be positive in a voltaic and negative in an electrolytic. The other difference is the galvanic or the voltaic cell typically has two cells or chambers versus an electrolytic. We have typically like a single cell. So in this case, you see this image, we just have a porous screen between the two. We don't have two distinct chambers. All right, so with these electrochemical cells, this is just an example FRQ, and a lot of students immediately saw this and they're like, what is going on with that diagram? Don't worry about that diagram. Jump right into the actual question. You're focusing on just writing the net ionic equation for the most favored reaction, so the reaction that's going to have the highest cell potential. All right, this is another thing. So cell potential, how do we calculate it? It's going to be equal to the cell potential at the cathode minus the cell potential at the anode. Again, this is not on the formula sheet, but it's a really simple equation. So definitely one to memorize. The higher the cell potential or the more positive, the more favorable that reaction. In Unit 9, you're also going to get into free energy. So the Gibbs free energy, it's just another way to calculate this. It's going to be equal to negative NFE. We did some practice with this at the beginning of this video, but just keep track of those units. All right, and this is just additional practice. If you want to check this out, this is just from the 2018 exam. Sometimes it is as simple as recognizing that you just need a salt bridge to balance charge. That is it. Oh yeah, no, let's talk about this. So standard versus non-standard conditions. So a standard electrochemical cell, we have concentrations of 1 molar, we have 1 atmosphere of pressure for gases, and a temperature of 298 Kelvin. So the cell potential is dependent on the concentration and the pressures of those reactants and products. So if we change any of those things, then we have a non-standard cell. And we can't use Le Chatelier's principle because we're not at equilibrium. Because again, if we're at equilibrium, we have a dead battery. Not an ideal situation. So this is another situation where you have to think, okay, if A changes, how's that going to impact B, which eventually impacts C, right? So at standard conditions, Q is 1 because the concentration of the products and the reactants is 1 molar, right? They're both equal. That's 1. So when the concentration of the products increases, E is going to decrease because when the products are numerator increase, Q increases. When we subtract that, right, our cell potential now decreases. Versus when the concentration of the products decrease or our reactants increase, E is going to increase because Q decreases. So it's a matter of like thinking, okay, if this one change happens, how is that going to impact everything? And how do I know this? The Nernst equation, which thankfully is on your equation sheet. You're never going to have to actually calculate a distinct value, but you are going to have to know how the relationship changes. So again, look at Q, see how Q is going to impact as Q increase, because if Q increases, then the cell potential decreases, and going from there. And this just, again, is just a little bit of an overview with that, so you see all the different situations. But again, I think if you really understand what's happening with that Nernst equation, you don't need to memorize anything here to think about that. We also have Faraday's law and electrolysis in here. It's a lot of using stoichiometry. Again, we did some practice with this at the beginning of this video. I have tons of videos that will help with that. Again, it's just a matter of setting everything up so that we're canceling out all of those units. So when it comes to electrolysis, we can use Faraday's law to determine any of these things. So again, it's just a matter of making sure that we are canceling things out correctly. We're using the constants, making sure those units are accurate. And the really nice thing is you have unit conversions now listed. So the last two in that center column are going to be related to these types of conversions. So use those, rely on those units to get from point A to point B. So at this point, I want you to close up your notes and go to bed. I don't know when you're watching this. It could be 3 a.m. on Tuesday. Go to bed. Go get at least a few hours of sleep, please. That's more important than studying and memorizing molecular geometry at this point. Are you kidding? Let that one point go. Pack your bag. Be ready. Don't forget to eat. Have a good plan for breakfast. It is a long test. So make sure you have fuel for your body and your brain to get through that, so you're not jumbling over your words at 1 a.m. like I am right now. Get to your test site early if possible. Laugh, cry, celebrate this accomplishment that you've made it this far in AP Chemistry. I'm impressed that you took this course with everything else you have on your plate right now. And I want you to celebrate, surviving AP Chem. No matter how you feel on Tuesday, go out, have some guacamole, have ice cream, do something to celebrate surviving AP Chem this year. And when everything is released, hopefully on Thursday, I will post my roast of the exam along with a complete FRQ explanation video. So keep an eye out for that and make sure to tell next year's AP students or victims, depends on how you look at it, about my accounts. Thanks for watching and best of luck.